Hi everyone, welcome to Skill 24. We're going to talk about solving rational equations and inequalities, more specifically the inequalities piece. But before I do that, I want to take a moment to just kind of talk a little bit about a rational expression. So a rational expression is made up of a ratio of two polynomials. So if you look here, you'll notice there's a fraction bar, and we have a polynomial on top and a polynomial on the bottom. Okay, and if we look at this particular graph, this graph is the graph for this function g of x, okay? And what we're going to do is we're going to talk more specifically about the algebra for solving rational inequalities. But first, what I want to do, I'm going to skip some of what's here. I'm not going to get into all of this right now. What I am going to do first is make the connection of the function form to the graph, okay? So we're going to notice something happens in this function at -3 and also at +1. So let me explain that. So what I'm going to do is I'm going to factor the numerator and the denominator of this function, and we're going to talk about what we notice. So x squared plus 4x plus 3, that'll factor as x plus 3, x plus 1, because we're looking for two numbers that multiply to 3 and add to 4, so that's 3 and 1. For the denominator, we're looking for two numbers that multiply to -3 but add to +2. So that'll be x plus 3 and x minus 1, okay? All right, now going back to this graph, remember I said that there was a hole in the graph at x equals -3 and there's a vertical asymptote at x equals 1. So how does that get reflected in what we did just a moment ago? Well, if you notice here, these x plus 3's would end up canceling out. And from Algebra 2, for those that remember this, you may remember that when that happened, your graph has a hole in it. Okay? So, and the way we would look at that is, what is the 0 of that factor? Well, x plus 3 equals 0 when x equals -3. Okay, so the function is undefined there because we can never have a denominator value equal 0. But if you had a factor that canceled from top and bottom, that means that you're going to have a hole. Okay, so it is a discontinuity, but it's a less invasive one, if you will. Now, when I look at the other factors, I have x plus 1 on the top and I have x minus 1 on the bottom. Those don't cancel, so this remaining factor in the bottom gives us what's called a vertical asymptote. That's that line that was drawn here, and a graph cannot cross over a vertical asymptote. And that happens when x minus 1 equals 0, so x equals 1. Okay, so at x equals 1, we get a vertical asymptote. So looking at our graph, that's exactly what we see at x equals 1. All right, so then the only thing that's left is this piece right here that was not canceled out of the numerator. So x plus 1 equals 0 when x equals -1. That's going to end up being the 0 of this function. So we can see it crosses the x-axis there. So at x equals -1 rather, we have a 0. So g of x equals 0 at x equals 1 because the leftover factor in g of x is x plus 1. G of x is undefined at x equals -3 and x equals 1. At x equals -3, that is the canceled factor of x plus 3. And x equals 1, that is the uncanceled factor in the denominator. Okay? So essentially, when we are solving a rational inequality, we're going to have to do some factoring, and we're going to have to figure out the zeros, and we're going to have to figure out where we might have a hole and where we might have a vertical asymptote. Okay? So the rest of this video is going to be just showing how to solve these things. Okay? So let's say, again, we have this same function. So we already know how this will factor. It'll be x plus 3, x plus 1 over x plus 3, x minus 1. We already know those will cancel. So the simplified function for this is x plus 1 over x minus 1. So we'll keep that in mind. But what we have to know is that we have to consider that we would not be allowed to have x plus 3, well, the 0 for that, we're not allowed to have that in our solution when we solve an inequality or an equation. So let's say I wanted to know, well, when is this function less than or equal to 0? Well, what we are going to do is we are going to, we already factored it, I did that up above. We're going to set each factor equal to 0 to find the 0. So we know that x plus 3 equals 0. Actually, we know it can't be equal to 0, so x can't be negative 3. We know that x minus 1 can't be equal to 0 because that's what's in the denominator, and that would cause a vertical asymptote. So we know x cannot equal positive 1. Okay, and we know that x plus 1 will equal 0 when x equals negative 1. That'll be an x-intercept. Okay, so what we're going to do is we're going to draw a number line just like we've done before. And we're going to identify those critical values. So negative 3, negative 1, and 1. And we're going to choose a number from each interval and determine the sign of each factor of the rational function based on the chosen value. Okay, so this is a lot like what we did a few lessons ago with the nonlinear inequalities. So I'm just going to pick, let's see, something smaller than negative 3. Let's use negative 4. Something between negative 3 and negative 1, I'll use negative 2. Between negative 1 and 1, I like to use 0. And a number greater than 1, I'll use 2. All right, so what we have to do now is we have to determine what happens with our signs of, I'm going to use the simplified function, and we're looking to see when it is less than or equal to 0. Okay, so if I plug in negative 4 for my x, I get negative 4 plus 1, so that's a negative number on top. And on the bottom, I'll have a negative number, and two negatives divide to a positive. In the next interval, if I plug in negative 2 for x, negative 2 plus 1, that's a negative, over negative 2 minus 1 is going to be a negative. A negative divided by a negative makes a positive. When I plug in 0, 0 plus 1 is positive, and 0 minus 1 is negative. A positive divided by a negative makes a negative. When I plug in 2 for the x, both of those factors are positives, and when you divide two positives, you get a positive. Okay? All right, so now let's see how this would look when I go ahead and put all this together. So we know from all of the setting of factors equal to 0, we know we can't be equal to negative 3. We know we can't be equal to positive 1. And for the x equals negative 1, that's an x-intercept. Because this says less than or equal to 0, we are allowed to include the point negative 1. So I'm going to put a closed-in circle here. Now, to answer the inequality, we want the interval that shows that we have less than or equal to 0. Okay, so in other words, we want to look for the negatives. So this was a positive interval, so that's out. This was a positive interval, that's out. This is a negative interval, so from -1 to +1, we'll have a solution. And then from 1 on, that is a positive interval, so that one's out. Okay, so my solution that solves this rational inequality is going to be the interval from -1 to +1. Okay, so that is how that is going to work. And if we look at our graph for this, we can see from -1, that's where I had the x-intercept, over to +1, which is where I have the vertical asymptote. This piece of the graph is what is below, less than or equal to 0. So the graph now verifies that our solution is correct. All right. So now we're going to try another example. Notice this time the function is completely factored. So what we're going to do is first observe, oh, we do not have any holes, so no holes. But we know that this x plus 2 can never be equal to 0. Oh, I wrote -0. So we know x cannot equal -2. But what's going to be different this time is that we're going to have two x-intercepts. So x plus 1 equals 0 and x minus 1 equals 0. That means we're going to have x-intercepts at -1 and +1. Okay? So now what we're going to do is we're going to make our number line. And on our number line, we're going to put those critical values in order from smallest to largest, and we're going to find our numbers that we're going to use in each interval. So let's see, over here I use -3. When you have an interval that does not have an integer in between it, you just have to go with the decimal that's in between. From -1 to 1, I'll use 0, and from 1 on, I'll use 2. Okay. Now, none of our factors canceled out in the original form, so what I'm going to have to do now is just use all of that. But the nice thing is, in our denominator, we have something squared. So no matter what kind of number I put in for x, when I square that, the denominator is always a positive. Okay, so what I'm going to do is on top, I'm going to have two factors to consider, and on the bottom, we know it'll be positive. Okay. All right, so now what we're going to do is we're going to test our values. So -3 plus 1 is negative. -3 minus 1, that's also negative. The numerator, two negatives multiply to a positive, so it'll become a positive over a positive, so the whole region's positive. When I plug in -1.5, -1.5 plus 1, that's negative. -1.5 minus 1, that's also negative. Two negatives make a positive, and when you divide that by a positive, that's also positive. Plugging in 0, 0 plus 1 is 1, so that's positive. 0 minus 1 is negative, so that's negative. My numerator, positive times a negative is a negative. Negative divided by positive makes that region negative. And then going to the 2, both of those on top will be positive. Denominator is always positive. All those are positive, so that region's positive. Okay, so now how do we determine our answers? Well, I'm going to go back to my original inequality. It says just greater than 0. So these x-intercepts we found, those are equal to 0. So I'm going to use open circles on -1 and +1. And then what I'm going to do is I am going to, let's see, -2 is where we had a denominator 0, so that'll never work. So now I have to look at, this just says greater than, so we're looking for the positive regions, okay? So I go from -infinity to -2, and then I go from -2 to -1. I don't include the interval from -1 to 1, but from 1 to infinity, I can include that. Okay, so now I have my solution. Now let's look and see how that plays out in the graph here. The negative infinity to negative 2 is this part right here. The negative 2 to negative 1, that's this section right here. And then the 1 to infinity, that is this section right here. Those are the parts that are greater than 0. Okay? All right, in a second video, I am going to model how to solve some of these problems out algebraically. So this first video is kind of more conceptual. The second video, I will model how to do a few examples. Okay?